All right, you pick platinum. We'll put platinum here. What happens? Tell me what happens here. If you pick platinum as the anode, what are you going to put inside the solution? Zinc 2 plus or zinc? Zinc 2 plus. Okay. And what else? What else are you going to put in here? Just only zinc 2 plus? Yeah? What's the reaction? Well, where did the electrons come from? Nowhere. Therefore, can you use it? Well, you might get tricky and say, you know what I'm going to do? I'm going to attach a piece of zinc to my platinum, and I'm going to call the platinum the anode, but there's going to be a chunk of zinc solid attached here. If there's a chunk of zinc solid here, will platinum act as the anode? Do you guys remember the nail? Do you guys remember the nail? This would be like galvanized platinum. Do you want galvanized platinum? No, because even if you call platinum the anode, it's not going to be the anode. What's going to be the anode? You see? No other way around it. You have to have zinc. Okay. All right, any other questions? What?
Which is larger E of oxidation, negative 0.12 volts, and negative 0.12 volts.
Which one's going to have a larger oxidation potential? Is that the question?
Which is larger? Yeah,
Which is larger? Which one is larger?
The negative 0.82.
No. Negative 0.12 volts. Negative 0.12 volts is larger. Why? This is like asking what's a higher temperature, you know, negative 10 degrees C or negative 5 degrees C. You know, negative 5 degrees C would be a higher temperature. It's not asking you which is a larger voltage. Which is a larger voltage? Negative 0.8. You'd be right if I were asking what's a larger voltage, but I'm not asking what's a larger voltage. I'm asking what's a larger oxidation potential, right? What would you rather be shocked with? Negative 8,000 volts or negative 1 volt? Negative 8,000 volts because it's smaller than... well, this is a concept you... Then if you confuse yourself, you don't have it down. You know?
Can you say the example again? The one that you said?
Which would you rather be shocked with? A voltage of negative 8,000 volts or the voltage of negative 1 volt? Negative 1 volt? Because why? Yeah. Right, negative 1 volt because it's a smaller voltage, right? Negative 1 volt is a smaller voltage than negative 8,000 volts. Which one is a smaller voltage? Smaller voltage. No.
0.12 is smaller.
Smaller is 0.12. Then, you know, right now it's kind of late to get this concept down, so, you know, this is one question.
But it's asking which one is larger.
I don't want to spend 30 minutes on this because we talked about this many times. So let's skip it. Let's move on. Other questions? Because I have to talk about chapter 25 too. Although, you know, the one thing on the final, maybe this is what hurt people on the final. This is something I noticed. Because initially, I made the multiple choice kind of not worth so many points, but, you know, on this last test, they were worth 3.5 points, although I put an extra one on there. On the final, they're going to be worth, like, something around there. You know, 60 questions, close to 200 points or so. Not exactly 200 points, but... No, each question is going to be like 3-pointer. 3-pointer. And on the final, I don't give, you know, it's either right or wrong on the final. And so maybe that's what got people last. And so be careful in answering the multiple choice, you know, on the final especially, because you want to make sure you don't make a simple mistake. No, it's still the same. Yeah. It's just the bulk of the points are multiple choice. Are there any other questions? The difference between these voltages is, you know, relative, what zero means, you know? That's the difference. We talked about what zero means, right? But, one has an absolute zero, the other is an arbitrary zero. When I asked you about getting shocked, what would you rather get shocked with? 0 volts or 1,000 volts? 0 volts, but 0 volts is nothing. That's absolute zero. There's nothing there, right? But what would you rather be oxidized by? A vat of acid or water? Well, you go a vat of acid because the vat of acid has 0 volts. So I'll take a bath in a vat of acid. This is a 0 volt potential, right? Is it? No, it's arbitrary 0. So this is something you have to drill. You know, it's like, okay, I heard it. Well, lots of people hear it, and then, you know, it doesn't stick. And so how do you make it stick? You got to put it in your own, you know, you got to think of your own kind of story to make up with it. You know, and I don't know, I can repeat the same thing over and over, but if it doesn't click, you know, oftentimes it won't click until you actually sit there and think of your own little analogy for this, you know. And then maybe it'll click. Al?
Were those two voltages, if they were in a standard electrode potential chart, would they have been flipped because they would have been E reduction? Like the negative, would they have been positive?
There's only one chart. It's either a reduction chart or oxidation chart because it's easy to figure out the opposite because you just change the sign.
But most of them are reduction charts, right?
No, well, up until the 1980s, they were all oxidation charts. Okay. And then after that, they switched to reduction charts. They're all oxidation charts, but you still see oxidation charts. If you ever look at the activity series in Chem 4, that's an oxidation chart, not a reduction chart. And so if you look at the Chem 4 activity series, it matches the oxidation potential chart. And so therefore, it was easy, you know, because in Chem 4 you see that, and then in Chem 1b you talk about the oxidation potentials. And then they switch it to reduction potentials. I don't know why.
I'm confused because most of the charts that we've been looking at are reduction potentials, and so a smaller voltage would have a higher oxidation potential. Correct? Or like more negative voltage. Because a higher voltage would have a better.
No, you don't compare. You know, if you're looking at the left side, you don't compare to the right side. All you do is you look at the left side and you know what the potential means, right? And then if you need to, you just rewrite the chart. Rewrite the chart over, you know, but don't think about flipping or doing anything like this. This is why I said don't do this. E of the cell is equal to E naught of reduction minus E naught of reduction. Don't do that, because that just confuses people. You know, and it's hard for me to explain this when people are thinking about flipping the sign. You know, it doesn't matter. It says the same thing. I mean, if you sit back and look at it, the charts are the same thing. If you rewrote the oxidation chart, it tells you exactly the same thing. You interpret the numbers exactly the same way as you do a reduction chart. And so, you know, a lot of people don't understand the numbers at all. You know, you'd be surprised how many people don't understand these numbers, like what 0 volts means in an oxidation or reduction potential chart. They have no clue. And so this is the only reason why I spent extra time on this, is because this is one of those things that people, it just doesn't click because they don't, you know, you just got to, all you have to do is you look at it over and over and over again. It's nothing impossible once you look at it enough times. If you look at it enough times, it'll just click, you know, eventually. And so the thing is, people don't look at it at all. People don't look at charts, you know. They just don't, because they think, it's not worth the time. Matthew?
Are there any formulas we should have memorized?
No. The formulas I'll give you. That goes for the final too. On the final exam, I'm going to give you the formulas. Yeah. And constants, right? Right, the Faraday constant, that kind of stuff.
Faraday constant.
Huh? I'm sorry? Amps? What I'll say is amps is equal to coulombs per second. You know, 1 amp is defined as 1 coulomb per second. I would say that. Yeah. A volt, I'm not sure if I'd tell you. Coulomb times joule. Right? Or, I actually, volt, I might not tell you. Because E is equal to NF, or I'm sorry, delta G is equal to negative NF E. Right, and so you're right, a volt is equal to joules per coulomb, not joules times coulomb, sorry. And so this I might not give you because I'd expect you to, I mean, I'd give you this equation, expect you to be able to figure out the units by dimensional analysis. Yeah, that's it. What was it? The other question?
Is graphite a strong oxidizer or a weak oxidizer?
Is graphite a strong oxidizer or weak oxidizer? Where did you hear graphite's a strong oxidizer?
I don't know.
So the question is, what is graphite? Is it a strong oxidizer, weak oxidizer, or whatever? What do you think? You should know because carbon, sp2 carbon. What do you think? Strong oxidizer? Weak oxidizer? It's not inert. It's almost inert. Yes. Almost inert. In fact, if you know, can you burn graphite? Well, you could try. You could heat it up until it's glowing red hot, but what tends to happen is it just vaporizes. Maybe a tiny bit will oxidize, but the graphite will just vaporize. The graphite, have you ever tried to build a fire using pencil lead? No? Or have you ever tried, why don't you try to catch it on fire? Or will pencil lead catch gasoline on fire if I put pencil lead into gasoline? And so it's not strong either way. It's not reactive. And so the answer is no. No and no to your question. Yep. That's why it's called, and I don't know how many times I wrote it as inert electrode, graphite, inert electrode, graphite, inert electrode, graphite. You know, the thing is, the only way that clicks is by repeatedly saying it, because some of these terms aren't so easy and are easily confused, right? And so the repetition does help, especially when it comes to these voltages, you know, high oxidation, high reduction potential. Okay, anything else?
Would you give us the chart?
Yeah, I'm giving you the chart. So. Nothing else? All right, then we can move on because I got to finish up chapter 25 before. A lot of people want some kind of, not too much, lecture on the last week. I keep it.
For 25, he's making what we did in class.
Okay. So what comes first? Does the hypothesis always come first? No, usually what comes first are observations and patterns. And so what we're going to look at is we're going to look at the patterns of nuclear stability. And we talked about nuclear stability, right? We can get a gauge of nuclear stability by looking at what? The mass defect per nucleon. And so if we look at this is the binding energy per nucleon. How do you calculate the binding energy per nucleon? Well, you look at the mass defect and convert that into energy, and then you normalize it by dividing it by the number of nucleons. And so what does this tell you? The greater the binding energy per nucleon, the more stable the nucleus is. And so if we look at it, the most stable nuclei have a mass number around 60. So they have about 60 nucleons. What has about 60 nucleons? Nucleons would be what has about 60 nucleons? Around here, right? Actually, is this about 60 nucleons here? Neodymium? Is that 60 nucleon? No. This is not. This is Z of 60. What would have around 60 nucleons? Tell me what element. Yeah, zinc or copper, nickel, cobalt, iron. These species are going to have the most stable nucleus. But you notice that the lighter elements have less stable, and the heavier elements are less stable. And so the most stable tend to be in the middle. And so in nuclear reactions, we want to go from less stable to more stable, right? And so let's take a look at some nuclear reactions here. There are two types of nuclear reactions shown on this chart. One is fusion. And so what is fusion? Fusion is fusing two nuclei together. And so let's take an A plus a B and fuse them together to get some kind of C. We can figure out if this is energy, favorable or not, based on the masses. And so if we look at the mass initial and the mass final, and so the mass initial will be the total mass of what your starting material, and the mass final will be the total mass of your of your final material. If we undergo fusion, that is, we're taking two lighter ones and making a heavier one, then which one should have a higher mass? Which one should have a lower mass? Yes. That is, your final mass should be less than your initial mass because some of that mass is going to be converted into energy. And so we can figure out the energy of this reaction. Delta E is equal to delta mc squared. This is the energy for this fusion reaction. Energy of the fusion reaction. Talk about it briefly here. So how do you fuse two nuclei together? Because the two nuclei are going to repel each other, right? They're going to repel each other because the electrical repulsions are so large. And so what you need are extreme temperature, high speeds to overcome that repulsion, and high pressures usually. So here, I mean, at least reasonably high pressures. And so the high temperatures are going to be reached in plasma, but this plasma has such a high temperature to vaporize anything that it comes in contact with. And so this plasma is contained by electric magnetic fields, which are generated by this confinement vessel here. And so what we're trying to do is trying to fuse two hydrogen atoms together. This is a deuterium, H2. Can you guys see this? This is a tritium, H3. And when you fuse these together, the combined mass of this is greater than the combined mass of this. We form a helium atom and a neutron in the process. All right, and so in this particular reaction, we can calculate the amount of energy here by looking at the mass difference. Once we figure out the mass difference, that's delta U converted into delta kilograms, plug that into this equation, we can figure out how much energy we're going to generate per atom of hydrogen. Actually, this was one of the homework problems, I think. All right. Let's shrink this down. All right, we could give an example of this. I just need the masses of these isotopes. Down here. Should have been here. So I got to get the actual masses of the isotopes. I'm going to go back to chapter 2 and get them from chapter 2. I'm not going to get it from our book. The easiest place to get these is from a table of isotopes. So it's pretty simple, actually. You can see the isotopes here. So we're going to take a deuterium and a tritium and make a helium and a neutron. And so the masses are just there. So let's calculate the energy of this fusion reaction here. And so the reaction again was deuterium plus a tritium yields a helium. Note something that happens here, plus a neutron. Neutrons are given the Z of 0 and an N of 1, a mass number 1. But if you look at this, the A's, 2 plus 3 is 5, 4 plus 1 is, and then 1 plus 1 is 2, and 2 plus 0 is. These nuclear reactions have to be balanced in this way, always. So we can figure things out. That is, the Z's have to add up on both sides, and the A's have to add up on both sides. And we know it's balanced. All right, so let's figure out the mass here. And so we have a deuterium, which is a 2.014102 U. We have a tritium, which is 3.016049 U. And so the total mass on the left is 5.030151 U. And then we figure out the total mass on the right. You know, helium-4 is 4.002603. And how much is a neutron? Does somebody have their book handy? I want to go back to chapter 2. All right, if not, it's okay. I'm going to get the neutron mass from chapter 2. It's like 1.06. Oh, no, 1.08. 1.0087. I don't know if that's going to be accurate enough or precise enough for us. 1.0087. And so we're going to be limited in sig figs here. So we're going to go 3, 0, 6 and 7 is 13, 11, 05. So take a look at what happened to the mass. The total mass on the starting is more than the total mass at the end. Yeah. And so there's a change in mass, which means that energy. And if we lose energy, you know, that's going to be exothermic. Energy is going to be released, right? And so let's go ahead and figure out delta M for this. Delta M is going to be just 5.0113 sub 03 minus 5.030151 U, which is equal to what? Can someone punch this out? The calculator. I don't want to do it, or maybe I'll just do it. 3 is 2 and 5, 2, 1. I think I just screwed it up.
Negative 0.016848.
0.16848.
Yes.
Okay, we're 1, 2, 3, 4. So 16848 U, correct? Okay. All right. Then we just plug it into our equation. The energy change, delta E, is equal to delta M, the mass change. And so this is just going to be minus 0.01648 U times we got to convert U into kilograms. So what is it? 1 gram is equivalent to how many U? 6.022 times 10 to the 23rd U. And then convert it to kilograms. Kilogram is equivalent to 1,000 grams. And then times C squared, 2.998 times 10 to the 8 meters per second quantity squared. That's going to give us how many joules of energy? Uh-huh.
You're just subtracting there, right?
Yes.
So on my calculator, I have negative 0.018847.
88? 88, okay. So fix that then. 8847. Right? 88.
No, it's point 0.01.
8847.
Yeah.
Thanks. Okay, how many joules of energy did you get? So it'd just be 0.018847 divided by Avogadro's number divided by 1,000 times 2.998 times 10 to the 8 squared. You know what? I have a calculator here. So let me do this. So 0.018847 divided by 6.022 times 10 to the 23rd divided by 1,000 times 2.998 times 10 to the 8 squared. 2.812 times 10 to the minus 12 joules. Is that what you guys got? Yeah. Good. 2.812 times 10 to the minus 12 joules. Is that enough to heat a cup of coffee? Would you even see a temperature increase in a cup of coffee? No. It doesn't seem like much energy, does it? It doesn't seem like much energy. Oh, no, the negative's still there. Negative just means it's released. So it's exothermic. So it's negative. So are we going to be heating much coffee from this nuclear fusion reaction? No. Until you realize that this is the amount of energy per atom. If I was interested in a mole of deuterium, you know how much a mole of deuterium weighs, roughly? A mole of deuterium weighs 2 grams. How did I know that? Because its mass is close to 2, right? And a mole of tritium weighs about 3 grams, right? And so let's take a mole of deuterium and a mole of tritium. That is about 5 grams worth of reactant. And so if we do this per mole, we'd have to multiply this by Avogadro's number. And so let's multiply this by Avogadro's number and then figure that out. So I'm going to times 6.022 times 10 to the 23rd, and I get this. I get 1 billion, actually not 1 billion, 1 trillion, 693 billion, 969 million, 114,000 joules. Can you heat up a cup of coffee with that? Yeah, that's just from 5 grams of reactants. Can you believe that? That much energy? So this is why nuclear chemists, I mean, if we look at the kilojoules, how many kilojoules is that? Well, that's still 1.6 billion kilojoules per mole. That's crazy amount of energy. Yeah, kilojoules or joules per mole. Just a crazy amount of energy. And so this is why it looks so promising, right? It looks so promising as an energy source. And the thing about this fusion reaction is the product. The product of this fusion reaction is just helium. And helium is inert gas, right? Has lots of uses. And so this would be good.
Is that what you do in nuclear plants?
No. Some, you know, the problem, there's one major problem, and that is the activation energy. The activation energy is out of this world. Hard. Yeah. Out of this world. And so unfortunately, the activation energy is so big that they have to input more energy than the output, or, you know, it's very close to break even, but still. Maybe they can figure it out. Somebody can figure out how to make tritium work. I mean, excuse me, this kind of fusion work. And so the problem with this is, even though it's exothermic, right? Let's go back. Even though it's exothermic, these fusion reactions are incredibly difficult to do. Okay, I mean, how do you fuse nuclei together? How can you overcome that activation barrier? Well, if you don't need to react that much, you know, if you don't need to react that much, then it's not that difficult to overcome that activation barrier. And that is, what you do is you just accelerate two atoms, you know, what they call atom smasher or something like that, just into each other, so they collide. And so this would be a linear accelerator. You know, this is a long line, and so you start off with atoms here and ionize them, and then just start accelerating them using electric fields, right, magnetic fields, until they reach very high speed, and then there's a collision. You know, just a few atoms. But a few atoms collision, is that going to generate much energy? Enough energy to heat up your cup of coffee? Probably not. You know, you need a lot of collisions to generate some decent amount of energy, right? And this isn't going to generate a huge number of collisions because it just isn't that scale, you know? This is just for atoms, atom smasher. And so using this, you can make, you know, different atoms. For example, this. This is what we call nuclear synthesis. And so you take two atoms and make bigger atoms. In this case, we're taking californium and nitrogen and smashing them together to make this one. I don't know what DB is, but DB260. Oh, what was that again? Dubnium? Dubnium? Okay. Okay. If you take this, Dubnium 260, is this favorable or unfavorable? We're taking a big one and a small one and making an even bigger one. Is that favorable or? That's unfavorable. But you can have this reaction go, you know, overcome that. It forms an unstable product which will decay again. And so you can make heavier elements like all these. All these were made, man-made, right? The transuranium elements were man-made by smashing, you know, two atoms together, but it's not stable, so it doesn't live very long. So these ones are the transuranium, neptunium, plutonium, etc. You're right, dubnium is it. It's an interesting name. But anyway, here, in this case, this would be favorable. Why would this one be favorable? And so this should be endothermic, this should be exothermic. This should be exothermic because we're taking two smaller ones and making a bigger one, right? And so this is a fusion. And so favorable. Do you see how they add up? 249 plus 15 should equal 261. 98 plus 7, 105. You guys see that? How they add up? And so this way we can figure out the puzzle for these types of reactions. Looking at how they add up, right? Over here, this is 24 and 1. This has got to be 25. So this must be maybe a hydrogen. But then this is 11, and this goes to 12. So yeah, it is a hydrogen. Here. And so we can find the missing one by just adding the things up, seeing what Z is here. The next pattern that's observed for nuclear stability is this. When you look at all the data, then you see that these are unusually stable. That is, when we have 2 protons and 2 neutrons, 8 protons, 8 neutrons, 20, 20, 28, 28, 50, 50, 82, 82, 114, 126, and then 184 for the neutrons. This has some stability, extra stability. And so, what do we call these? These are called the magic numbers. These are the magic numbers. That's the magic number pattern. The next pattern that's observed is this. When we look at these, we notice that when Z is even and N is even, there are more nuclids that are found. When Z is even and N is odd, there's quite a bit fewer. And so it looks like the nuclei that are favored are even. So even and even must be more stable than any other combination. The worst combination is odd, and it looks like Z even is better than Z odd. Do you see that pattern? This is called the even odd law or even odd rule. What would you say? Maybe even odd law or even odd rule? That's fine. It's just another pattern that's observed. This is the next pattern that's observed. The next pattern that's observed is, it also depends on the neutron to proton ratio. If we plot the neutrons here and the protons here, if we had an even number, that is the same number of protons and neutrons, it would just be a 45 angle line here. But it looks like we favor a 1-to-1 ratio for the lighter atoms. But as we get heavier, we favor more neutrons. And so it becomes like a 1.1 ratio. You want 1.1 neutrons to every proton. And that seems to be more stable. This is called the belt of stability, so they're just plotting out the isotopes. If you deviate from the belt of stability, then it becomes less stable, radioactive. And so if we're out here, outside the belt of stability, then we have too many neutrons. If we're over here and we have, then we have what? Too many too many protons. Well, if we have too many neutrons, how can we get rid of neutrons? Well, one type of method is by undergoing beta emission. What did I say beta particles were?
Electrons generated
In the nucleus. How do you generate an electron in the nucleus? You know how you generate an electron in the nucleus? You convert a neutron. If you take a neutron and spit out an electron, what do you end up with? A proton. And so in beta emission, a neutron gets converted into a proton plus a beta. And so we say it this way. A neutron, which is N01, gets converted into a proton, which is a 1,1, plus a beta. A beta has 0 for Z and its charge, a beta has -1 for its Z and a 0 for its mass. Do you see that, how it adds up? And so here, if we look at the proton, 1 minus 1 is 0, and 1 and a 0 is 0. And so if we have too many neutrons, we can undergo beta emission to convert a neutron into a proton. And so radioactive isotopes in this will have beta emission. Over here, if we have too many protons, do you know what we could do? We could do positron emission. And so what is positron emission? What is a positron? A positive electron. And so a positron would be a beta, not with a -1, but with a 1, and a mass number of 0. And so this must be plus a what? Neutron. And so here we convert a proton into a neutron via positron emission. And that gets rid of some protons. Or electron capture. What is electron capture? It's when the nucleus captures an electron. If the nucleus captures an electron, like this, it'd capture an inner shell electron. Nucleus captures an inner shell electron. Well, electron is going to be -1, 0. What is that converted to? A neutron. If it captures an inner shell electron, then the outer shell electron is going to drop down, and typically we get a gamma ray from this, but you don't have to know that. No, electron would be attracted to the nucleus. But how would it get there, you know? Oh. So those are some additional types. And so we can answer questions like this, you know, based on the patterns. Just patterns. And do we have to know the theory to make predictions? No, we can make predictions just based on these patterns. Right? Because it's just patterns that fit the existing patterns. And so here, you know, which would be stable, which might be radioactive. A list of nuclei. Does it? But really, what do we want? We don't just want patterns. We want, ultimately, we would want what? Theory. And so what kind of hypothesis? You've seen the patterns for nuclear stability. What kind of hypothesis now would you generate? Based on the observations that you saw. about nuclear structure, the structure of the nucleus. You know, how are the protons and neutrons arranged in the nucleus? How do they behave? Because we want to make predictions, like we want to predict what is the mass, you know? Right now, in order to figure out the mass, could we calculate it? No, the only way you're going to figure out the mass is by measuring it. And so we want something where if somebody says, I have 6 protons and 6 neutrons, what's the mass? And so we need the theory. Well, in order to get to the theory, we've got to first formulate some kind of hypothesis, right? And so what type of hypothesis can you think of? Well, I'll tell you the hypothesis here. This kind of looks similar to what? You've seen these magic numbers before with the periodic table, you know? The magic numbers in the periodic table would be 2, right? 10, 18, 36, right? Those magic numbers in the periodic table correspond to what? Shells, filled shells of electrons, right? Not 10. And so over here, the hypothesis is this, that the nucleus should consist of shells, protons and neutrons. Does that make sense? Yeah? And so this is called the shell model of nuclear structure. But you know, the hypothesis and theory comes from the observations. Right? Observations are going to be the facts. Well, anyway, let's move on to this and look at nuclear reactions. Do you see this one? U-238 is unstable. It's big. All big nuclei are unstable. And what do they want to do? They want to break up into smaller. And so this is, what is this He4 called? It's alpha particles. So this is called alpha emission. Part of the nucleus just gets spit out. 2 protons and 2 neutrons. And this is highly exothermic here. This would be favorable. This is called fission. Fission is breaking apart. Fusion is fusing it together. And so big atoms like this undergo fusion spontaneously. Well, unfortunately, thorium is still radioactive itself. And so thorium is going to undergo fission as well. And so this is a typical fission reaction. Here we have a beta. Beta emission we talked about is converting neutrons into protons. We have too many neutrons. Nu would be energy. So the thorium here undergoes beta emission here. And so we can figure out what forms. If this were blank, we'd have to have 234 on top. And then 91 minus 1 gives us 90, so this has got to be Pa. Here's phosphorus 30. Phosphorus 30 is a light element, but it's radioactive. Phosphorus 30 undergoes beta emission. Here we just don't have enough neutrons, so we go to silicon 30. Next is electron capture. Here, this element captures an electron. So 81 minus 1 gives us 80. 202 and 0 gives us 202. So it's going to be Hg followed by X radiation. Maybe I overestimated the energy. I overestimated the energy. If the valence electron comes down from the core, it's not going to emit a gamma. It emits an X-ray. Here, this double dagger just means an excited state. It spits out a gamma here after this alpha emission. But we aren't going to worry about this. Alpha followed by gamma. So how does an alpha particle get out of the nucleus? You know, how does a beta particle get out of the nucleus? How is an electron captured? You know, so many questions to answer. Right? And so how are alpha particles, how do these get out? The answer has to do with quantum theory and the nature of forces involved. Let's continue. We'll leave it at that. This has something to do with tunneling. All right, so if you look at your homework, you don't really have to do much other than just predict this. And so here, 86 means this must be 84. Element 84 is, just look it up down here, polonium, and then 222, this must be 218. So it's polonium 218. And so this is the type of thing you'd be expected to do. All right, I'm going to stop here and then we'll continue this later. See, we'll take a break. Do you want your last exam after or before? Before? Okay. Before your test. After the test? Yeah, you can get it after the test. If you want it before. Your last test. If you want it now, you can get it during the break here. Yeah. We're going to have the test after the break. Yeah, you could use that one. Cecilia, were you waiting? Yeah. too.
Did you ever find the other paper?
No, I need. That's right. Before the test, I'm gonna. I just want your list of unknowns that you found. Do you know?
Oh, okay.
Let's see. Stephanie. Natalie. See.
I just want to get
All right. Anybody else?
Well, it's because it's not right. Because like this lithium ion wants to become lithium metal. You know what does it? Because if it becomes lithium metal, you know how unstable lithium metal is. It wants to get rid of the electron really bad. Right? Even in air, it goes up. It's because just because it's fluorine, it's just because it's plus one.
any things that you write on the board that you clear up. Can you email it? Because the girl who answers the phone, she doesn't really know chemistry, so she kept coming in and asking me. She wasn't really sure what she was writing was right.
Oh, okay, I'll email it.
and then they can just print it and give it to me.
Yeah, that's better.
Instead of her writing it, because she wasn't really sure if she was writing it down right.
Yeah, I was.
And what it meant, so she kept asking me. I was like, well, I don't really know what he's telling you.
Okay, that's better. Yeah, I'll email it. I didn't know that option was available. Otherwise, I would have emailed it earlier. Oh, sorry.
I'm not sure whether it is there's an external power source. Not to apply
The mixed heroes off the.
I think one is like storage.
Yeah, I got it mixed up with the other class, but let's see this right now. Okay, it'll just be a minute.
Yeah, we want to help with
You wrote out the table. It's like you would have to
Did you talk about chapter 14?
Yeah, I don't have it with me right now. Get it later. I'll give it to you.
Can I get out the class?
Yeah.
This one
You can get out.
it's liquid, right? Number 2. Just because it's liquid doesn't do about those numbers because this number cannot compare.
No, this is not liquid. This is aqueous. Yeah.
Aqueous because it's just aqueous solution, right?
Yeah. It's aqueous, so this.
But how can we know? We didn't know the number. These two numbers are not comparable.
I know they're not comparable, but you should know that a solid versus a aqueous solution should have a. They're the same species, almost. Aluminum versus Al3 plus. Could be organized, right? But aluminum is a very simple metal, so it's going to have a low entropy. Oops.